But
Okay, let's go in now.
thank you. Okay, so today we're going to do section 2.5. If you would follow along in your syllabus, this is the last section of 2.5 that I will cover in class, but you will be responsible for section 2.6. In the syllabus it says to be read on your own. It's one of those concept sections that you can do fairly easily on that you can understand it, but it is an important section. It's about basically it's how to lie with statistics, how graphs and things like that can be misleading. So we'll leave that for you to read. There is a homework set online over that section too. It only has a couple of questions. So section 2.5 is called measures of position. And let me get my PowerPoint up. And this is the same one you've been looking at, so I just want to be able to show the distribution of different data that we collected. Let's see, I got to get computer 2. Yeah, there we go. So measures of position, what we're referring to there is for an individual value in the data set, where is that value in relation to the rest of the distribution? So far we've talked about the shape of the distribution, we've talked about where the distribution is centered. So this one we would say is centered at about 72. This is the pulses. We've talked about measures of the spread of the distribution. How spread out is it? Is it flat and wide, or is it skinny and tall? So spread of the distribution. Today we'll get another measure of spread, but mostly we'll get measures of location. Okay? So think about, a good way to think about this, to start this discussion, is standardized testing. Right? Now remember when you wanted to go to college, you had to take, I thought you were taking a nap there. You had to take the ACT test. Remember that? And you remember you got your scores back and it broke it down for you how your score related to the rest of the nation. In particular, it divided it into math score and verbal score and whatever else. Remember when you got your math score back and it said you were at the 99th percentile? You remember that? No. I remember it said 40th. Hopefully they didn't say that. But let's say it said you were at the 90th percentile. That's a measure of position. All right? What position is that? So the notation that we use is P, capital P with a sub 90 or sub 80, whatever percentile that you're interested in. So this is called the 90th percentile. So what does that mean? To say your score was at the 90th percentile. Exactly. You did better than 90% of the people who took the test. Okay? So another way to say that is 90% of the distribution is below that value. So percentile is not a percent. It's a value from the data set that has a certain percent below it. So here is the distribution of pulses. Right? The mean pulse was in the middle there, about 72. Okay? Do you remember what the standard deviation of pulses was? If you don't remember, I can hit page down and it'll be listed there. 10.3. So I'm going to call that 10. It's not what numbers I can round and do in my head fairly easily. Standard deviation is about 10. Now just for a little bit of review, if I went out 10 units, one standard deviation from 72, that puts me here at 82. And one in the other direction takes me to 62. If I draw dotted lines up to the distribution, what proportion of the population should be inside there? 68. So 68%, or as a proportion, 0.68. Okay? And that's from the empirical rule. Okay? So, we can use the empirical rule to help us estimate some of these percentiles. Tell me what percentile is the number 82? If you turned in your pulse and you said, my pulse is 82 beats a minute, what percentile would you be at? The answer is not the 68th percentile. That's most people's first guess here. That's not it. But it's on the way to getting there. What? Nope, not 78th. Okay, we're thinking about, remember what percentile is? It's the number that has that percent below it. So to figure out the percentile of 82, we have to figure, well, what percent of the distribution is below 82? Well, we know that 68% is down to here. So what we got to do is figure out, well, how much is on down below that? Almost. He said 32, and that's not quite right. 32 is how much is not in here, right? Some of that that's not in here is down here, and some of it is up there.
16.
16, good. So this is 0.16. Because it is a symmetric and bell-shaped distribution, this works. Whatever's not in the middle, you divide in half, and put half in the lower tail and half in the upper tail. So I got 16% in each of the two tails. Now, what percentile is 82? Not 16. What'd you say? 84, good. That is P84. Now, if you're thinking, huh? Well, you're just adding these two numbers together. 0.68 plus 0.16 is 0.84. So that's the 84th percentile because it has 84% below it. Yeah?
And how did you get this number?
This number? This is half the, quote, leftover percent. Okay, so I had this percent in the middle. How much is left over? 100% minus 68%, that's 32%. So then I take half of that leftover percent and I put it down on the left side, and half I put up in the right side. Got it? All right? Now when I said got it, almost all of you did this. So let's see if you got it. What percentile would 92 be? Do that one on your paper, and I'm going to come around and look at your paper. And if you don't get it right, I'm going to laugh. Not really. But if you don't get it, then as I come around, say, I don't know what to do here, or what do I do now? Ask questions. Okay? If you can do it in your head, great, but don't shout it out. I had to tell a guy to shut up this morning. Okay, is this sign-up sheet, is it hit you guys? Is it hit everybody? Everybody been on the sign-up sheet?
No.
Oh, Logan came in late. So actually, he would be responsible if he's here to get it started, but. Okay. You know where to start?
I think so.
Pretty much you always start with that picture. you draw that normal bell-shaped picture, start labeling things, and I always start with these dotted lines because they give me my markers. I can figure out where they are because they're halfway down the hill, right? And then I know that 68% is in there. I want a number, or I'm sorry, I want to find out what percent is below 92. That's what I want to figure. To know what percentile it is, I need to know what percent of the distribution is below it. So start using your empirical rule and doing just like we did with one standard deviation. Now how many standard deviations are we? 2. Because we said standard deviation was 10, and I'm sitting at 92. From 72 up to 92 is 2 standard deviations. That was a good hint on how to work this. You got it figured out yet? Okay. I'll give you one hint. It is not the 95th percentile. Good. Answer? Yeah. Okay, that'll actually work. Yeah, you do. Keep thinking, you'll figure it out.
Anybody got it wrong yet?
Anybody what?
Has anyone got it wrong?
Got it wrong? No, nobody has an answer that they have written down. Most people just don't have an answer.
I wrote down.
Okay, this is incorrect notation. I'm going to stop that right now. What I want to know is 92 is equal to P sub question mark. Right? So 92 is a full stop, not the percent. And that's real common to get those mixed up. Nope. That's a good guess, but it's not right. Got an answer yet? Good, you got it. Teach your sister now. Good. Good. Bad. No, just kidding. She's kind of stuck. She hasn't got a wrong answer, but she's kind of stuck. Okay, are you ready for me to do it? Did I look at yours? Do you have an answer? Do you have an answer?
Maybe.
Maybe?
I have an answer, but I don't know if it's right.
Nope, that is not right. And that's not right. In fact, you did the same thing she did. You put the 92 in the wrong place. Oh no, I'm sorry, you didn't.
I did.
Yeah. Yeah, you did. I had you guys backwards. It's not P sub 92. It's kind of, and I saw somebody actually write this, which I like. P sub question mark is 92. What percentile is 92? So we're trying to figure out that question mark. Okay? So here we go. Well, I guess I don't really need to even erase. Well, I'm going to erase this 0.16 right there. I'm going to draw a vertical line above 92. And I'm going to come down and draw one above 52. Right? Now, in between there, in between those two lines is what percent of the population? 95% by the empirical rule. We got 68, then at 2 we have 95, and at 3 we have 99.7. Right? So this one is 0.95. So do the same thing we did when we worked this one. You take what's in the middle, you take 1 minus that, and that's the leftover percent. So what's 100% minus 95%? 5%. Or 0.05 if you're doing proportions. So where does that 0.05 go? You split it. You take half of the leftover percent, and it's now going to be down here into that tail. So how much is that?
0.025.
Half of 0.05 is 0.025, and half on this end would be 0.025. Now if I add those three numbers together, 0.025 plus 0.95 plus 0.025, I get 100%. I got the whole distribution. So how much is less than 92? 97.5%. This 95 plus this 2.5.
Would
You got
round-
9. What's that?
Would you round to 98 or just keep it?
I would keep it as 97.5, but people laugh at me when I try to say that. That's the 97.5 percentile. Yeah, how do you say that? The 97.5?
97.5.
Yeah, 0.5%, I don't know. But anyway, yes,
How do you find your .95?
empirical rule. You're just supposed to have that memorized. So here you go. It's 1 standard deviation plus or minus 1 is 0.68 or 68%. Then plus or minus 2 standard deviation is 0.95. And plus or minus 3 standard deviation is 0.97. I'm sorry, 997. That's the empirical. So once you know the empirical rule, or better yet, once you have the empirical rule on your cheat sheet for the test, right, then you can always figure out percentages as long as they're nice multiples of standard deviations. Yeah,
How big is the cheat sheet, by the way?
full-size sheet of paper.
Front and back?
Front and back. You can put anything on there you want, which I highly recommend a few example problems. Right? And the day before the test, I always have a review test that we go through. So a lot of times people take problems off of that as example problems, and that's a good suggestion. I've seen people, I don't know if I recommend this, but that have access to a copy machine that has nice reducing high resolution, and they'll reduce that practice exam down so small they get the entire thing glued onto the side of one sheet of paper. You're allowed to do it. You can do anything you want. But I literally, this is a true story. One time I had a woman who was taking my class, and she did that to such extreme that you couldn't read it. And she came in with a magnifying glass. And she had her cheat sheet and her magnifying glass. Now, here's the question. Do you think she did well on the exam?
No.
No. Why not?
Takes too long.
Too much time looking through that darn cheat sheet instead of learning it before she came in, right? The idea is by the time you fill out the cheat sheet, you remember it and you don't ever need to look at it. That's the plan. But it's there just in case so you don't have that anxiety. What if I forget? Well, if I forget, then I go look at the cheat sheet. Okay. So that's percentiles. So once we have percentile defined, and I never did write the definition down, but it's just the percentile is the value that has that percent of the distribution below it. There are some others that, some of the percentiles that we give special names. For instance, P50. That gets a special name. What is P50?
Half.
The 50th percentile has half the distribution below it. What's that called?
Median.
By definition, you go halfway through, you're at the
Median.
median. So the P50 is the median. Right? P25 is called the first quartile, which we will abbreviate with Q sub 1. And then P75 is Q3, the third quartile. If you want to divide your population or your data into fourths, that's quarters, so quartiles. And it takes 3 divisions to do that, right? If I want to cut my distribution into quarters, then I have to have 3 cut points. And those three cut points are called the quartiles. And the median, by the way, is the second quartile. That's such a cool number, it gets three names. It's P50, it's the median, and it's the second quartile. But it's all of those things. So in a symmetric bell-shaped distribution, that's at the mean. They're at the same place. But in a skewed distribution, the mean and the median won't be at the same point. So, I erased part of my line there. This was at 62, and this was at 82. Now, see if you, let's test your insight of this. Now don't shout out the answer as soon as you think of it. Let everybody think about it for a minute. I'm going to go over there and I'm going to mark where Q1 and Q3 are. Where will they be in relation to 62 and 82? Because those numbers are one standard deviation on each side. Will they be inside of those, so in here, or will they be outside of those? Think it through. You have all the information you need to answer that question. Naomi, right? What do you think?
Outside.
Outside, okay? And Logan, you said?
Just inside.
Inside. So I got one vote each. Kate, what's your vote?
Inside?
Inside? Are you guessing?
I thought about it.
So it's an educated guess. Good. Chelsea?
Outside.
Outside. We're 2-2. Garrett?
Inside.
Inside. And Marianne?
Outside.
3-3. Well, let me ask you this. How much area is in between these two? 68%. How much area is in between Q1 and Q3?
50%.
50%, right? Because you divide it into quarters. So there's 50% in there. So to get 50%, do I go wider or do I go narrower? Narrower. They'll be inside of there. Okay? Let me hit page down, and the computer will tell us what they were.
78.
It's kind of hard to read. I got to do some erasing here. But there's Q3, there's Q1. So over here is 78 and 65. And the median was 70. Okay? So let me go back to the picture. And 65, there's 64, halfway would be 66, so 65 would be right there. And 78, this is 76, that's 80, so 78 is right there. So there are my quartiles with to there and there, 0.5. Half of the distribution is in between them. Okay? Now that distance, which is Q3 minus Q1, that distance is called the interquartile range, the IQR. Okay, so let's go back to the output, and you'll see right here it says interquartile range 13. So that's 78 minus 65. So I'm going to write that here. 78 minus 65 is 13. That's the IQR. Okay? The IQR is a measure of what? Spread. Very good. a measure of spread. A big IQR means it's a long ways between the 25th percentile and the 75th percentile. If it's a long ways between them, that means your distribution is pretty flat and spread out. If they're real close together, then most of the distribution is really close to the middle, so you've got very little spread. And notice that the IQR is a number that's a little bit bigger than the standard deviation, but kind of in the ballpark. And it's always that way with symmetric bell-shaped distributions. It's always a little bit bigger than the standard deviation. Okay? Now, these 5 numbers, I can't write on this one up here, but this one is the max, 104. And then these 3, Q3, median, and Q1, and then the min. That's 5 numbers, and those are known as the 5-number summary. Okay, so I can read them right off of that for pulse, so I'm going to bring them over here so that I can change that screen and still have them. The minimum values down here at the bottom. And that is 42 right there. So the minimum value, the minimum pulse was 42. Q1 was 65, the median was 70, Q3 was 78, and the max was 104. Those 5 numbers give you a pretty good idea of the distribution. But in order to get a picture of the distribution, we can take those 5 numbers and make what's known as a box plot. Okay? Now the real name of this is a box and whisker plot. And I like that name better because I like to say whisker. You draw a box and then you put whiskers on it. So here's how it works. You draw a number line. My marker's going a little weak here. Let me get it different. You draw a number line. Then you make sure that you label the number line so that it can accommodate your min and your max, so that everything will fit in there, right? So my min is 42, so if I start at, say, 40, and then I'll go 50, 60, 70, 80, 90, 100, and 110. Now, I wasn't perfectly accurate in my distances there, but I'm not going to grade your artwork as long as it's on the ballpark there. On an exam, I would probably give you a number line that has evenly spaced hash marks, and then you can label them however you want. Then your art can't be as bad as mine. So the first thing you do is you start with the 3 in the middle, Q1, the median, and Q3. And you draw a box out of those. So the left edge of the box is Q1. So if this is 40, 50, 60, 65 is right in the middle, and I'm going to draw the left edge of my box, just like that. Then I'm going to go to Q3 and draw the right edge of the box. And that's at 78. So this is 65, 70, 80. So 78 would be just almost to 80. And then you make a box out of it. So this one is at 78, this one is at 65. Now the median is marked inside the box. It's at 70, so you draw a vertical bar at the median. Okay? Now the whiskers come off the box on either side, and guess where they go out to?
Min and max.
To the min and the max. So the min was at 42, so that's about right there. I'll draw a whisker like that. And then the max is at 104, so this is 80, 90, 110, so 104 is about right there. Okay? Now that, when you look at that, with a trained eye, you can look at that and go, oh, that's pretty symmetric distribution. You can't really say that it's bell-shaped from a box plot, but at least you can say it's symmetric or not. It's symmetric because the median is roughly in the center of the box and the whiskers are roughly the same length. Let's do the box plot for age. Oh, by the way, your calculator will do a box plot. It's under stat plots, which is in yellow or blue above the Y equal button. But in order to do it, you have to enter all the data into a list and then have it compute this 5-number summary. And for a data set this big, it's not practical. I can't ask you to enter 385 numbers into a list into your calculator. But if you have a fairly small data set with 30 or 50 observations, then you could probably handle that. But for the most part, software is going to do this kind of thing for you. And with a box plot, it's actually about as easy to produce it by hand as it is to try to use your TI-83. So I don't really even teach that. Same thing with histograms. It's in there, but you can ask if you want to learn how to do that. So let's do the same thing. I'm going to go to the same page, but for age instead of pulse. So let me page down. And remember, there is the distribution of age, a highly skewed distribution. If I show the summary statistics, then the max is at 81. So max equal 81. Q3, I'm going upside down the way I did over there, but that's not important. Q3 is 37. The median is 22. And Q1 is 20. And then the min was a 15. The min was supposed to be what? 18, because you weren't supposed to ask anybody less than 18, but we had a few people that did. And so the minimum that I actually got was 15. So let's do the box plot of that guy. I'm going to do it underneath this one. So what's the first step?
The marks.
Okay, put the marks on. Label the number line so it will accommodate your min and your max. I need to go from 15 up to just past 80. So if I go, I'm going to start at 10 and go 20, 30, 40, 50, 60, 70, I'll stretch it out a little bit, 80. Okay? So then we draw, what do we draw first? Okay, we draw the box, and the box goes from Q1 to Q3. So Q1 is at 20, so I'm going to draw the left edge of the box. Q3 is at 37, so this is 30, that's 40. So 37 is just back a little ways from the 40. There's my box. Okay? Then where does the median go?
In the box.
It goes in the box. So this is 20, so 22 is just barely past that, about right there. So this was Q1, this is the median, this was Q3. Now the whiskers, off the min is 15, so I draw a whisker out to 15, and the max was 81. This is 80 right there, so just past that. Now, do you see the difference? What a symmetric distribution looks like in a box plot and what a skewed distribution looks like in a box plot. So you can look at a box plot and go, ooh, we got a skewed distribution here. Okay? Now, in a real extreme case, I don't have any data like this to show you, but in an extreme case, suppose we have like, how about we ask a survey in college and we say, how many times have you been married? Right? And what'd you say, Marianne? 0. 0. How many people in here would say 0? Almost everybody. So what's my data set going to look like? If I drew a histogram of it, big spike at 0, a few ones. By the time you're a college kid, you probably haven't been married twice. But there might be a few people. So maybe a tiny little bar at 2, and beyond that, probably nobody. Yeah.
Well, would that be just like regular college students or
Traditional or non-traditional?
traditional or non-traditional?
Well, it could be all college students. So you're going to get a few, that are coming back and they're 50 years old, they're going to college, and they've been married 3 times. But it's very few. So you get a big spike at 0 and then a long tail. So you're going to get a skewed distribution, right? Well, when I said how many people have been married 0 times, about 3/4 of you raised your hand. So what's the median of that data set going to be? 0. What's the 25th percentile going to be? 0. What's the 75th percentile going to be? 0 if 3/4 or more are zeros. So you can get a box plot that is what I call degenerative. It degenerates, so here's 0. You get your min, you get your Q1, you get your median, and your Q3 all up there, and then you get a whisker going out to, maybe this is, I've been married 5 times. Right? So it kind of all collapses in on itself. And that's extreme skewness. But you'll see box plots like that occasionally. Okay, now what about outliers? What would happen to the whisker if we had one big outlier? It's going to take the whisker out and it's going to distort your idea of whether or not it's a skewed distribution. Suppose I had that one meth addict, right? And I had a pulse of 120. So instead of stopping at 104, it's going to go out here to 120. And now you look at that and you go, ooh, we got a skewed distribution. Look how much longer that whisker is. But really, you don't want to have that misleading idea of what it looks like. So we can draw what's known as a modified box plot and label outliers. So here we go, outliers. We'll find outliers using what we call the 1.5 IQR rule. So low outliers are going to be values that fall more than 1.5 IQRs below the box. Right? So in the box plot here, you say, okay, here's the width of my box. By the way, how long is this box?
13 units.
That's the IQR, right? It's in this case 13 units. So the width of the box is the IQR, not the IQV. The IQR. So think about taking 1.5 of those. So 1.5 would be about like that and going below the box. Does it look like I'm going to have an outlier? Well, it's kind of behind my hand there. But yeah, 1.5 of those below the box. Put me at about right in there. Right? Well, here's how that works. Below the box is to the left of Q1. So low outliers, you identify Q1 minus 1.5 times the IQR. So let's plug in the numbers. Let me get on the screen back up to the pulse. The Q1 was 65. So I'll have 65 minus 1.5 times the IQR, which was 13. Okay. There we go, fresh batteries.
Oh, 6.
Okay, so this number, what did you say it was?
45.
45.5?
45.
45.
45, and you said that, and I wrote
I
44.
said 44 because I was doing the math wrong in my head.
Okay, well, don't do that. Okay, so 45.5 is our cutoff for low outlier. So this is what I call the cutoff. Anything less than 45.5 we'll consider an outlier. Do we have any numbers that are less than that? Yeah, we have a 42. I'm not sure if I have any more than that, but actually I can tell right here that the first percentile is 46. And so, and if you look at the histogram, you can tell there's only one that's below that, and that is the 42. So we have one value that's a 42. So what you do is you stop the whisker at the last non-outlier. So this is going to stop at 46, and you put an asterisk at 42. Now you don't stop at 45.5. You stop at the last non-outlier that's in your data set. So even if maybe maybe I had this 42, but then I had a 52 was my next to the smallest number, then I'd stop it at 52. Even though I was allowed to go all the way to 45.5 by the cutoff, you stop at the last non-outlier, and then you put an asterisk for the outlier. Okay? Now let's go off the upper end. For high outliers, you want the same idea, but you want to go 1.5 IQRs above the box. So where do you start?
Q3.
Q3, very good. So Q3, and this time instead of subtracting off, I'm going to add 1.5 IQR. So Q3 was 78. 1.5 times the IQR was 13. Interquartile range. It's this guy. Okay, now, who's got that number?
97.5.
How much?
97.5.
97.5. So that's my cutoff for a high outlier. Anything that's bigger than 97.5, I'm going to call an outlier. So again, if you look at the numbers here, I see that I have a max of 104, I have a 99th percentile of 100, and then the 95th drops down to 89. But I'm going to need to look at my histogram to see how many outliers I have. So here they are. And actually, you would go to the data set, or the software would tell you all of the values that are above that. But you just go to the data set and say, print out all the numbers that are greater than 97.5. But here I'm just looking at the histogram, so I only can get a rough idea. But this is 96, so this bar is at 98. So I don't know how many 98s there were. A 98 would be considered an outlier. It looks like this has 4 in it. It's a fairly tall bar. And then this one has, I think that looks like it's about 5 people. This is about 4 people, and this is 1 person. Let's say that, and this is there's a bar right there. That's a 102. That's a 104. And let's say there's 3 100s. And again, these probably aren't going to exactly match what's in the data set, but it'll be fine for our purposes. So this is 100 right there on my number line. Where do I stop my whisker?
98.
I would stop it at the last value we have that's less than this cutoff, and that's going to be a 96, right? Assuming there weren't any odd numbers up there. So I'm going to stop this thing at 96, and then anything out beyond that will be flagged as an outlier. So we probably have a 98, we're going to have a 100, we've got a 102, and we've got a 104. And there may be multiples of those. It looks like we've got 3 100s. So sometimes you'll do, I'll stack them up like that to show that there's more than one here. Because if you just And the software would just put the asterisk right over the top, and you couldn't tell there's two of them there. So it would look like, well, there's 3 or 4 outliers, when really there's more than that. But the fact that there's kind of a cluster of numbers called outliers tells me there's a little bit of skew in this data. Off this end there was only one, but off this end there's a cluster of 6 or 8 outliers. So there is some skew to this data. But this is known as a modified box plot. And it's modified to show the outliers. Now I'm going to show you this. This is hard to see.
Plus it was mean.
Yes, the plus is the mean. This is females and males for height. Okay, so it's a box plot of heights. Look at the females. Does it appear to be a fairly symmetric distribution? Yeah. These are what I used asterisks, these are the outliers. The software is using boxes, and you can tell it to use whatever you want. We had a 51-inch and a 53-inch tall woman submitted. Right? So those are outliers. The box is very symmetric. The median is right in the middle of the box. The lengths of the whiskers looks good. Right? This is a side-by-side box plot, which lets you see not only the distribution for males and females, but also how they compare. And you notice the men are shifted up, which tells you men are tall. Okay? So these are stood vertically, and I've been drawing them horizontally, but it's the same idea. For the males, we had one outlier off the low end that barely passed where the cutoff was. And that was, well, I can't really tell what it was. It looks like it's about 65 or 66 inches tall. The top had some outliers. Right? There were at least 4, but it's possible that some of those boxes are stacked on top of each other. So there's at least 4 outliers off the top. The top one is our 84-inch tall guy, or 7-footer, right? And then we got an 81 and some that are smaller. Now the plus sign is the mean. Well, I didn't show doing that at all, and the book doesn't go into that, but a lot of software will do that. They'll mark not only the median, but they'll mark where the mean is also. Because that's a good indication of skew also. If it's perfectly symmetric, where do the mean and the median lie? At the same spot. If you get skew or you get outliers, it will pull the mean towards it. So our outliers up here pulled the mean up above the median. The low outliers for females pulled the mean down below. If you get a lot of skew, you'll end up with this kind of a look in a box. I'm doing a vertical one. If you get a lot of skew, you'll get like that, where the median is off center in the box and the mean is a long ways away from it. Okay? Okay, I ran out of time without getting to z-scores. But I think you have one homework problem that talks about z-scores, so you'll need to look at that yourself. And I'll cover it again. I'll cover it on Friday. But z-score is the last measure of position that we'll talk about. So we will see you on Friday. We will. Yeah. Not for a little while, but.